All right, rational functions. So a lot of this, really, there's only one new concept in this, and that's how we're going to describe asymptotes. So this is a lot of building on what we already know when we analyzed functions, okay? And we're specifically talking about one kind of function, and that is a rational function. Do y'all remember what rational functions are when we graphed them?
Yeah.
Okay, kind of. No. Okay, it's whenever we have something over something. It's a fraction, essentially, is what it is, okay? And remember, we talked about several things with the fraction. The parent function here is 1 over x. That's our parent function for rationals, all right? And so we talked about, let's see, we talked about a lot about asymptotes when we were talking about rational functions, okay? And we were looking at the degrees on the top and the bottom. Do y'all remember that? And so we said for horizontal asymptotes, this is where we looked. Is it top heavy? Is it bottom heavy? Or are they equal? And what am I looking at again? I know, but what's what's telling me? What's telling me if it's top heavy, bottom heavy, or equal? The what? The degree. The degree of the top versus the degree of the bottom. Okay? Do y'all remember this a little bit?
Yeah.
Okay. So if it was top heavy, it didn't have any horizontal asymptotes. Right? And if it was bottom heavy, do you remember what the asymptote was? Oh my goodness, y equals 0. We're talking about the equation, we're talking about an asymptote, right? And then we said if they were equal, we took the coefficient of the top divided by the coefficient of the bottom. That's exactly right. I really wish my pen would work today. Coefficient, top, coefficient. Oh no, my internet's not working. Is that light blinking?
Yeah.
Hampton. All right, tell me how I found, that's how we found horizontal asymptotes. And what we're really going to do is kind of tweak this definition of asymptotes, because a lot of you asked what are asymptotes, and I kind of dodged the question just a little bit about, because when we get here, we really talk about the definition of an asymptote and what it means, okay? All right, so horizontal asymptotes, there's how we decide. How about vertical asymptotes? How do we decide where vertical asymptotes happen? And I'm just recapping here for you. Do you remember? Vertical is up and down, right? So it's x equals something. How do you find that asymptote?
That's a good question.
We find where the bottom equals 0 because that's where it's undefined, right? Can't be there. All right. So let me talk to you just a second. We're going to define asymptotes the same way we define in behavior. We're going to use some limit notation. I know, y'all are so excited. All right, so let me start with a graph. I'm going to say defining asymptotes. Let's say I have f of x equals 1 over x minus 2. As far as asymptotes go, tell me what you know. Go ahead. Is it top heavy, bottom heavy, or equal? It's bottom heavy, right? So it's y equals 0. You're exactly right. Okay? Are there any vertical asymptotes? Yes. Where? At what? What's the equation of the vertical asymptote?
Negative
Close.
2.
Positive 2. right? It's where the bottom would be 0. So my vertical asymptote, I say, okay, well, where is x minus 2 equals 0? So it is at 2. All right, so without actually making you graph it, this graph actually looks something like this. But here's what we're going to do. We're going to define the behavior of the graph at the asymptote. All right, so what I want to do is I'm going to say, okay, first let's do end behavior. The limit as x approaches infinity of f of x, what does that equal? Look at the graph. As you look to the right, what is the graph doing? It approaches 0. Do we all see that? So the limit as x approaches infinity is 0. Do we all agree? Okay, what if I look at the other end? What's the limit as x approaches negative infinity? 0 again. Do you see that? This is the definition, the textbook definition of a horizontal asymptote. Okay? When you have the limit that approaches a number like this, okay? I should write this. Let me go to the other page to write the definition for you, and I'll come back to this. Because remember, we're defining what an asymptote is. So a horizontal asymptote happens when the limit as x approaches negative infinity equals a number. Okay, so it's, oh no! No worries. So if it equals a number one way, or, bless you, as you approach infinity, positive infinity, the point is that if the end behavior, okay, doesn't equal like positive or negative infinity, it just equals a number, okay, then that tells me it has a horizontal asymptote at that number. So there's your formal definition. So do you see why on the one we just did, that has a horizontal asymptote at 0? You can still find them the way I've showed you to find them, but when we define it, and it says define the asymptote, this is how we define it. Okay? It has an asymptote at y equals 0 because the limit as x approaches negative infinity is 0. Does that make sense to everybody? Okay. So we're going to do the same thing with the vertical asymptotes. And they're a little bit harder. Please work, pen. So looking back at our graph, we said it does have a vertical asymptote, right? Where the bottom equals 0. And that vertical asymptote is 2. Go back, what, to the definition? A little bit tricky, okay, because as I look at my vertical asymptote of x equals 2, right? I'm going to put a VA. I can't describe the end behavior this way, left and right, and it have anything to do with that vertical asymptote, right? So what I have to do is I have to describe the behavior of each piece here that approaches the asymptote. And so the way I do that is I say, what is the limit as x approaches, what's my asymptote? 2. But now what I do is I put a little negative sign here. Can you guess what that means? This means as you approach 2 from the left, okay? So anytime I have the limit as x approaches some number, we'll call it b. This way, this means from the left. How do you think I say from the right? With a plus, right? So it would be, if I say, come on, the limit as x approaches b plus means the limit from the right. So So you tell me, what is the limit of this function as I approach 2 from the left? Close. From the left, negative infinity. Does everybody see why? Look at my graph. Okay, this is from the left. So on the left side of 2, what is the graph doing? It's going down. How about the limit on the right side? Positive infinity, because it's going up on that left side. Does that make sense to you? All right, so that's the formal definition then, and I'll give it to you with variables, of a vertical asymptote, okay? You have a vertical asymptote at x equals whatever that number is if, I'll give y'all a second to copy that down, then I'll write the definition. So our definition then of a vertical asymptote is any time the limit as x approaches some number from the left, if you get positive or negative infinity for that, okay? Or, and it doesn't have to be from both sides, it just has to be from one side when that happens, okay? Because you can have an asymptote that just restricts a piece of the graph. So, or the limit as x approaches a from the right side is an infinity, then it tells me there exists a vertical asymptote there, okay? So if you look at a graph, it's basically saying that it's getting really, it's what we've done, it's just saying it mathematically. It's getting really close to a number the further you go. That's all it's saying. Limit notation makes sense to you here. Okay. Let's do an example. Okay. All right. For example, that's an x, by the way. I have this function. Did I use the same one?
Yeah.
Oh, no. Okay, hold on. Let me change it. I even wrote down the examples I wanted to use. Yeah. Yeah. All right, 2 over x plus 3. There we go. And so what I want is I want you to identify the horizontal and vertical asymptotes, and then use limit notation to describe them. Huh? And what? Yeah. You need to use it? Did you get signed out? So, tell me what you know. Right now, we're just going to look at horizontal and vertical. Why is it y equals 0? It's bottom heavy, right? How about vertically? Yes. Okay. Let's graph it, because in order to do the limit notation for the asymptotes, you really need to graph it. Okay, so let's graph it and see what it looks like. So I got y equals 2 divided by x plus 3. And I'm going to graph it. Okay. Horizontal asymptote at 0? Yes. Vertical asymptote at -3? Yes. Right? That confirms graphically. So I'm going to sketch a graph of it. Zero. It doesn't have to be exact, because remember, I'm talking about in behavior here, right? So it's going to do something like this. Yes. Yeah, they help you to see the asymptote, since we're talking about asymptotes here. All right, define my horizontal asymptote using limit notation. The limit as x approaches what? Negative infinity, because this is where we use the infinities here, of f of x equals 0. That right there justifies to me that there is a horizontal asymptote at 0. Okay? Let's look at the other end. How about as x approaches positive infinity? What's it go? 0. Look at the graph. Positive infinity to the right. What does the graph do all the way to the right? It's getting closer and closer. It's approaching 0. Both ends are approaching 0. Does that make sense? No? All right. Approaches positive infinity means look at the right end of the graph. This is essentially, this is just in behavior like we've already done. Okay?
Yeah, I got that. But you said so. Okay, so we just doing one for one.
And then we'll do vertical. You need both ends, okay, because there could be more than one horizontal asymptote. In this case, it's the same one that's restricting both ends of the graph. This end right here is hugging 0. That's the left end. This is the right end that's also hugging 0. And they could be different. You could. Yeah. But now when we get to vertical asymptotes, this time we're going to approach the -3 from the left and from the right, and we're going to see what happens. So the limit as x approaches -3 from the left is what? So as I get closer to -3, this direction, what is the graph doing? Negative infinity, because it's shooting down. But as I approach -3 from the right, it's going up. That's exactly right. All right, one more thing to show you and I'm done. One more. Sometimes you can have what, you need me to go back?
Yes.
I'll go back a second. That's why it's important we graph, but again, you can use your calculator to look at that and analyze which way it's going at that asymptote from the left and right. All right, so sometimes we may have what we call a slant asymptote, which is a line that is not horizontal or vertical. And sometimes, like I said, we could even have a parabola that acts as an asymptote. Okay? And so here's how we find that. If we start out, and this always happens when we are bottom heavy. Because what kind of asymptotes do bottom heavy have? Y equals 0. Right? All right. So when it is, oh gosh, I told you wrong. It's top heavy. I'm sorry. I was sitting here going, that's not right. Top heavy. Because it's no horizontal asymptote. I'm sorry. My bad. Scratch that. All right, top heavy. So when it's top heavy, here's what we do. I have this equation. This is fun, I think. I think you'll like it. We hope. I know, this pen's acting up. All right, I've got this function, right? So I know horizontally I said none because it's top heavy. Vertically, what is it? Or, right? If I set the bottom equal to 0 and I solve, positive or -3. But now, hang on, okay, vertical asymptotes plus and minus 3, right? So now, what I have to look at, I have to look to see if it has what we call a slant asymptote. To do that, are y'all ready for this?
think she meant to put synthetic.
Well, if it'll lend itself to synthetic, you could, but this one won't, okay? So what we're looking for here, okay? We're looking for what you get when you divide, not including the remainder, okay? So we're looking for the quotient up here is what we're doing. So we're going to do x squared minus 9 into x to the third. I don't have an x squared. Most of these are not going to be hard division problems, so don't start getting freaked out on me, okay? They're going to be fairly easy. All right. What do you multiply x squared by to get x cubed? X. I get x to the third minus 9x, and I subtract. Okay? That is my remainder. Because there's nothing I can multiply x squared by to get 9x. I'm not interested in the remainder. I don't care about the remainder. What I care about is this. That tells me that I have a slant asymptote, bless you, at y equals x. Okay? So I've got positive 3, negative 3, and then I've got the line y equals x as an asymptote. Okay? So let me show you what it looks like on a graph. Y'all got that? We won't worry right now about the end behavior on a slant. Just worry about the end behavior on horizontal and verticals. What was I lost my equation. Oh, x to the third. Be careful with your parentheses as you graph them. Divided by x squared minus 9. All right. Look at what's happening here, okay? Because I want you to see exactly how these are asymptotes. Let me see if I can. Where's my annotate thing on here? Here it is. All right. Negative 3. Positive 3. The line y equals x is like that. See how it's restricting those ends that way? That's a terrible y equals x line. Okay, do you see? It's just holding the ends, different parts. You have different asymptotes that impact different parts of the graph, okay? But they are asymptotes because it's approaching that. It's getting close, but it's never crossing. But that's how we find it. So the big thing I want you to take away from today, limit notation for vertical and horizontal asymptotes, and how to find slant or other asymptotes by long division. Okay? Let me give you your assignment. Oh, I have to get out of this first.